draw a picture for ourselves so that we know what's going on. So we're given that we've got a spring tied to a mass. The mass is 3 kilograms. The spring constant is 10 newtons per meter. And let's say this is the equilibrium point. So let's call that x equals 0. By definition, the spring force at this point is 0. And it said initially this mass is displaced or removed from its equilibrium position by 2 centimeters. So this means this would be 0.02 meters, right? That's 2 centimeters. And now the mass it was pulled there, it's in rest, and now it's let go. We can assume for now there's no friction on the surface. We will treat friction a bit later. And because this mass was let go from rest, the initial velocity is again 0. And now we must calculate. And our system is just the spring and the mass. So anything that's not the spring or the mass is outside of our system. Okay, so let's calculate the potential energy of the system when we've got that x is equals to 2 centimeters. So if we were to remove the spring, if it were to suddenly disappear, that mass would just sit there where it was. So somehow the spring has got a reservoir of energy that can be converted to kinetic energy of the object. Now we know how this should look like. The potential energy of the system is basically equals to the elastic potential energy of the spring. And we know that this is just equals to 1/2 times kx squared. Right, that's when we looked at the work done by a spring, we found that this quantity of 1/2 kx squared is what changes. So we associated that then with the potential energy of the spring. So the potential energy of the system initially is 1/2 times spring constant is 10 newtons per meter. X is 0.02 meters squared. And the answer that we get is 0.1 joules. So you can check me up with the calculator if you want. Make sure that I didn't miscalculate. What should it be? Remember to take the square of 0.02. 0.002, so drop to 0. Sorry. So you say this must be 0.002, but with the half. Okay, let me just quickly double check. Yeah, you're right. This is then actually 0.002. You're right. Pretty sure that's it. Right, let's have a look at the kinetic energy of the system at this point. Because we've got initial velocity of 0, we've got no kinetic energy. So that's 0 joules. Let's look at the elastic potential energy when we now have this block has moved to 1 centimeter from equilibrium. So x is equals to 1 centimeter. Then our potential energy of the system is equals to a half times kx squared. In this case it would be a half times 10 times 0.01 squared. So let's do this by hand. 0, that's half, that's 10. This would be 0.0001. So this is a half times 0.001 if we multiply in the 10. So it's 0.000. Oh, sorry. There we go. Just see if you agree with my calculation. If we square that, we get this. Multiply by 10, so basically move the decimal one back, but divide by a half. Right, does that make sense? Okay, let's look at the kinetic energy of the system. Well, again, we have to start. The only thing we've got to get us the kinetic energy is the work kinetic energy theorem. If we look at our mass, there's a force acting on it from the spring, and the only effect that force has is to accelerate the mass, so to give it more velocity. So we must calculate the total amount of work done by the spring over this displacement from 2 centimeters to 1 centimeter. Now this is equals to, we've derived this, it's equals to a half kx initial squared minus a half kx final squared. And this is equals to then the change in kinetic energy of the system. So this will be a half times 10 times 0.02 meters squared minus a half times 10 times 0.01 meters squared, because this is where it initially was, this is where it ends up. So this is then equals to, we've already got this number actually, it's just equals to that, so that's 0.002 minus, we've also calculated this number already, it's just what we've got there, minus 0.0005. And this then is equals to 0.0015. So that's the change in kinetic energy of the spring, or of the mass. And since we had the initial kinetic energy as being equals to 0, here we find that the final kinetic energy therefore is equals to so many joules. And you can now go and have a look. If we just, here we had the system right at the beginning, and so we had that the energy of the system, which is all mechanical, is equals to the potential energy of the system plus the kinetic energy of the system, and this is 0.002 joules. Over here, we've got that the mechanical energy is equals to potential energy plus kinetic energy. Here our potential energy is 0.0005 joules plus the kinetic energy is 0.0015 joules, which is again 0.002 joules. So it seems like the same rule is valid throughout. Again, for this system, which has got nothing to do with gravity, we have that the mechanical and the potential energies, or the potential and kinetic energy gives us a mechanical energy, And this total energy, this mechanical energy, it does not change as the system evolves in time. How much of it is kinetic and how much of it is potential changes with time, but at any point if you add the two up, you must get the same number. Now the interesting thing here is there's definitely an external force over there, because the wall is not part of our system. And from the point of view of the spring, there's a force acting in that direction, keeping it from ripping free of the wall. But because this force has got no associated displacement, so that force from the wall does not displace anything. It doesn't do any work. Similarly, we've got this mass will have a weight, mg, it will have a normal force n. These are also these are also external forces because the surface on which this mass slides isn't part of our system. The system is just a spring and the mass. So the force from the surface on the mass is an external force. The force from the earth pulling down the mass is also external, but in neither case does any of these forces do work. So we can modify our initial conclusion saying that the mechanical energy of a system is zero if all the forces, let me just get a new pen. So if all the forces doing work are internal, so between objects in the system themselves, and also conservative. Just to give you also the unofficial definition of conservative and non-conservative forces, just to keep that in mind. The work done by a conservative force depends only on the starting point of the motion and the end point of the motion. So we already have two examples of this. We know that the work done by the spring force is, for example, a half kx initial squared minus a half kx final squared. So the work done depends only on where we start and where we end. Doesn't matter what happens in between, really. A non-conservative force is exactly the opposite. So a non-conservative force is a force where the work done actually depends on the path taken in between. So something like friction is a good example of a non-conservative force, because the longer the path is you drag something over a rough surface, the more work you have to do in total to counter friction. So anytime you see an expression like this, so something that just depends on an initial position and a final position, you know the work done by whatever force produces this is, that force is going to be conservative.